How's it going, ladies and gentlemen? Mr. Johnny here. We're going to take a look at phase changes. What is going on when ice melts, and why is ice water always 0 degrees Celsius, regardless of how much ice you put in it? If you got water and you got ice, it's always going to be 0 Celsius. All right, go forward. There you go. So let's take a look at a chart. So we have temperature over here, and we got time over here. So here we're heating stuff up, right? And the question is, well, what's happening during this phase change right here? Why is the temperature staying the same? What's going to happen there? So what might be helpful is looking at some phase diagrams. So we're starting over here at A, and it's a solid. So we know that those particles are locked into place and they have the regular structure and definite shape. Now at B, they're going from a solid to a liquid. It's melting, right? So what's happening is we're going from those things being locked into place to them breaking apart and being able to flow past each other. So they're no longer in a definite shape. They're not locked together. They can move around, and that takes energy. So if we keep adding energy, what's happening is that energy is going to spread those particles apart from each other instead of making them shake faster. Remember, temperature is kinetic energy, so it has to do with movement. So the energy that we're adding isn't going to make these shake faster, it's going to spread them apart. So right here, the kinetic energy is staying the same, but the potential energy is going up because we're adding energy to spread them apart. So once all of them have been broken apart and it's completely melted, then we got the liquid phase where they're moving around and flowing past each other, and then the temperature can go back up. So in this section C, the kinetic energy is going up, but the potential energy is staying relatively constant. It's not really changing. So in section D, we're going from a liquid to a gas. So we're going from them being like this, flowing past each other, to completely spread out and not being attracted to each other at all. They're just doing their own thing. They're gas particles. So the reason that it's flat here is the same reason that it was flat in section B. All right, the energy isn't going to move the particles faster. It's going to spread them out. So we got to go from the liquid, where they're still really close to each other, to spreading out. So what's happening is those particles are being separated with that energy. They're no longer next to each other. All right, so let's go back here. So in section A, if temperature is going up, kinetic energy is also going up, and the potential energy is staying the same. In section B, since temperature is constant, the kinetic energy, that's not an E, dummy. Kinetic energy is constant, and the potential energy is going up. For C, since temperature is changing, kinetic energy is changing, and the potential energy is staying the same. D, kinetic energy, the temperature staying constant, so kinetic energy doesn't change, but the potential energy goes up. And in section E, so since we have an increase in temperature, we know that's a change in kinetic energy, and the potential energy is staying the same. So let's take a look at these charts and try and fill them in, some graphic organizers. So gas particles, here we want a particle diagram in this space right here. So we can draw them all spread out, not attracted to each other. Liquid phase, they are close together and they can flow past each other. They take the shape of their container, whereas solids, they have a definite shape and locked into place. So some of these I'm hoping you know right off the bat. So let's go from a solid and work our way up. If we go from a solid to a liquid, what do we call that? We call that melting. Liquid to gas, you can call it a couple things. You can call it boiling, or you can call it vaporization. Vaporization's the better one, if you had to pick one. Boiling is when all the particles are trying to vaporize at the same time. Vaporization is just simply liquid to gas. And going backwards, gas to liquid is condensation. It's what happens on the outside of your cold glass. It looks like it's sweating, but it's actually not. And then liquid to solid, you guys probably know is freezing. All right, so there's these two other ones, 5 and 6, that you may not be familiar with. So when we go from a solid to a gas, we call that sublimation. Right? This is what dry ice does. Why is it called dry ice? Because it goes from solid straight to a gas and it doesn't go in the liquid phase. That's why it's called dry ice. Then there's also the opposite, going from a gas to a solid. We call that deposition. And if you look, the root of that word is kind of deposit. So that kind of makes sense. Going from a gas to a solid, that's like depositing something. Call it deposition. So now here, if we're going from solid to a gas, our particle diagram over here, temperature over time, remember it's going to start as a solid, heat up. Once it hit its melting point, it's going to flatten out. Temperature's not going to change until all of it's melted. Once it's all melted, then the temperature can go back up until it hits its boiling point, and then it's going to boil, stay the same temperature until all of it's a gas. Once it's all a gas, the temperature can go up again. So thinking about this, is it endothermic or exothermic? Well, we're adding energy in order for these things to happen. So that's going to be endothermic because we have to put energy in, and that's a positive delta H. Now going the other way, we start at a gas, we start at the high temperature, and we cool it down till it starts to condense, and then once all it condenses, the temperature will go back down. Everything's a liquid. It can go back down again. Once it starts to freeze, it stays the same temperature till all of it's frozen. Once it's all solid, and then it can go back down again. So what's happening here? Well, if we had to put in energy to go from a solid to a gas, we're going to get energy out going from a gas to a solid. So it's releasing energy. We call that exothermic. That's why steam burns. You put your hand over a hot teapot and it's boiling and the steam's coming off. What's happening is that really hot gas, water vapor is hitting your skin and condensing and releasing all of that energy into your flesh and cooking it. You don't want to do that. It hurts. Don't do it. All right, so positive or negative delta H? Well, it's a negative delta H because it's losing energy. So let's take a look at another example. Question 1 says, label the phases present in each line segment. So hopefully you guys got this, right? You go, all right, well, it's starting out at a low temperature, so that's got to be a solid. Then C to D has got to be a liquid, and then E to F would be a gas. All right, well, what's happening? What's present between B and C? Here we have solid and a liquid. Same with D to F, we got liquid and a gas during the phase change. What's the boiling point of this substance? Well, we know boiling starts right at B. So we got to go, all right, what temperature is that at? Follow it back. I would say that's about 375. But you know what? Let me call it 373. It looks like 373. It says, what is the melting point of this? All right, you follow that back and you go, that's about 273, I would suspect. So now we're left with the question, well, how much energy does it take to go through these phase changes? And it depends on a couple of things. It depends on how much stuff you have. It depends on what it's doing. Is it, heating up? Is it boiling? Is it melting? What's it doing? And what is the substance? Because it takes different amount of energies depending on the substance. So for heating or cooling liquid water, which is, you'll see, it's kind of a common problem in regents chemistry, to use this formula from previous units. Q equals mc delta T, where m is the mass, C is the specific heat of water, and delta T is the change in temp. So example problems, how many joules are required to heat 10 grams of water 20 degrees Celsius? So we're talking about 10 grams of water going up 20 degrees Celsius, so we just plug it in. Q equals m, 10 grams, times C, which is 4.18 joules per gram degree Celsius, times 20 degrees Celsius. And look what happens with the units. Degrees Celsius cancels out, grams cancels out, and you're left with joules. So now it's just plug and chug, and you get 836 joules. If you don't remember this equation, it's on your reference tables. If you don't remember your specific heat of water, it's on your reference tables. So during the phase change, what's happening? Well, we can't really use this equation, can we? Why not? Well, this delta T during the phase change is 0, and we know it's not 0 overall, right? So we're going to have to use a different equation. We're going to use two different equations, Q equals MHF or Q equals MHV, where HF is the heat of fusion and has a value of 334 joules per gram for water, and HV is the heat of vaporization, and that's 2,260 joules per gram for water. Remember, different substances will have different HFs and HVs. Sample problem, how much energy is required to melt 50 grams of water? So melting 50 grams of water at 0 degrees Celsius. So this at 0 degrees Celsius is just saying we're at the melting point. We don't have to cool it down anymore. It's there. It's at the melting point. So we're going to have to use Q equals M, H. All right, so here's a little trick. Melting is going to be HF. So HF, whenever there's a solid, you use HF. Whenever there is a gas, you use HV. The way I remember it is fusion, I think of fusing two solid things together. So HF always for a solid. Vaporization, well, it's talking about vapor, it's talking about a gas. If you're working with a gas at all, use HV. So this one we're using Q equals MHF. M is the mass, so we got 50.0 times the HF of water, which is 334 joules per gram. Forgot my grams over here. And now you beep up, boop. 50 times 334 equals 16,700 joules. So that's your answer. Some more practice problems. Which of the following phases requires heat of fusion to accomplish? So remember, fusion, we have a solid involved. So we're going from a solid to a liquid. So which one of these things is showing it? You're going to have to look at this. Well, nope, this one is not it. Liquid to gas, no. Gas to liquid, no. Solid to liquid, heck yeah. Which of the following phase changes is endothermic? Remember, that means we're putting in energy. So which one of these things requires energy to happen? Solid to liquid. You got to add energy to melt stuff. Some practice math problems. So how much energy would it take to melt 20 grams of H2O at 0 degrees Celsius? Well, melt is going to be Q equals MHF because it's solid to liquid. So plug and chug, 20.0 times 334, and you get do another one. B, how much energy would it take to boil 30 grams of H2O already at its boiling point? So we're going to use Q equals MHV because we're vaporizing. So we plug and chug, 30.0 grams times 2260 joules per gram. Grams cancels out, and we are left with 67800 joules. Don't forget units. Okay, so you stay classy, and I'll see you in class. Bring some questions.